Let's talk about something fundamental. What is everything made of? And what gives it substance? You can look around you right now. You see a table, a cup, your own hand. All of it is stuff. It has weight. It has mass. It feels solid. But why? Why isn't it all just weightless energy, like light, zipping around and never settling down? For a long time, this was a huge puzzle for the people who studied the tiniest bits of the universe. They had a beautiful theory, a kind of instruction manual for reality called the Standard Model. This model listed all the fundamental particles we know about, like electrons and quarks, and it described the forces that govern them. It was incredibly successful. It predicted things with amazing accuracy. But it had a giant gaping hole in it. The math of the Standard Model only worked if all the fundamental particles had no mass. Zero. That was a big problem. We know things have mass, we have mass, the universe as we know it couldn't exist without it. If electrons had no mass, they would fly around at the speed of light. They would never settle down to form atoms. Without atoms, there's no chemistry, no stars, no planets, no water, no people. The universe would be a thin, chaotic soup of energy. So our best theory of reality was based on an idea that was obviously wrong. Something was missing. The theory needed a way to give particles their mass. This is where the Higgs boson comes in. It's the answer to that question. But to understand the particle, you first have to understand the idea behind it. The idea is that the universe isn't truly empty. What we think of as empty space is actually filled with something. You're an invisible, universal energy field. Think of it like a kind of cosmic syrup or a spiritual ether that permeates everything everywhere. This is the Higgs field. It was there a fraction of a second after the Big Bang, and it's still here now, in the room with you, and in the deepest voids between galaxies. Now, imagine this field is like a crowded room at a party. All the people in the room are the Higgs field. Different particles move through this field. A particle that doesn't interact with the field at all can pass through the room easily. No one talks to it. No one slows it down. It just zips right through. This is like a particle with no mass. The photon, the particle of light, is like this. It travels at the ultimate speed limit, the speed of light, because nothing is holding it back. It doesn't interact with the Higgs field. But now imagine a very famous person walks into that same crowded room. As soon as they enter, people cluster around them. They want to talk, to shake their hand. The famous person can still move across the room, but it's much harder. They get dragged back by the crowd. They have to push through the interactions. This resistance to movement, this drag from the field, is what we perceive as mass. A particle that interacts strongly with the Higgs field is like that famous person. It gets bogged down. It feels heavy. The top quark, for instance, is the heaviest known fundamental particle. It's like the biggest celebrity at the party. It interacts very strongly with the Higgs field. An electron is like a less famous person. A few people might stop to chat, so it gets a little bit of drag, a little bit of mass. But it can move through the room more easily than the superstar top quark. So particles have different masses because they have different levels of fame. They interact with the Higgs field in different amounts, and that's the core idea. Mass isn't an intrinsic property of a particle. It's a result of its relationship with this universal field. The Higgs field is what gives the universe its substance. So, where does the Higgs boson fit into this? In the world of quantum physics, every field has a particle associated with it. The electromagnetic field has its particle, the photon. The field that holds quarks together has its particle, the gluon. So if this Higgs field is real, it must have a particle too. That particle is the Higgs boson. Let's go back to our party analogy. The crowd of people is the Higgs field. Now imagine someone whispers a rumor at one end of the room. A little cluster of people forms to hear it. That cluster then moves across the room telling other people, and the cluster of excitement travels with it. That moving clump of people, that disturbance in the field, is the Higgs boson. It's not one of the particles moving through the field. It's an excitation of the field itself. It's a little piece of the Higgs field balled up into a particle. Finding the Higgs boson, therefore, wasn't just about finding a new particle. It was about proving that the entire Higgs field concept was correct. If you could create and detect a Higgs boson, it would be the ultimate proof that this invisible field filling all of space is real. It would be the final piece of evidence that our understanding of mass was right. And that's why finding it became one of the biggest quests in the history of science. This quest was not easy. The theory predicted that the Higgs boson would be very heavy. And because it's heavy, it's also very unstable. It decays into other lighter particles almost instantly in a fraction of a trillionth of a second. You could never see one directly. It's like seeing the splash a rock makes in a pond without ever seeing the rock itself. You have to infer its existence from the ripples it leaves behind. To create something so heavy, you need a tremendous amount of energy. Albert Einstein's famous equation, E = 2, tells us that energy and mass are two sides of the same coin. You can convert energy into mass. If you smash two smaller particles together with enough energy, you can create a new, much heavier particle, like the Higgs boson, for a fleeting moment. This is why scientists needed the Large Hadron Collider, or LHC. The LHC is a massive machine built by CERN, the European Organization for Nuclear Research. It sits in a tunnel 100 meters underground, straddling the border between France and Switzerland. The tunnel is a 27-kilometer ring, a giant racetrack for particles. Inside this ring, two beams of protons are accelerated in opposite directions to 99.9999991%, the speed of light. They circle the ring thousands of times per second, gaining energy with every lap. Then, at specific points in the ring, the beams are steered into a head-on collision. When these protons smash into each other, their energy is released in a tiny, incredibly hot fireball. For a brief moment, the conditions are similar to what the universe was like just after the Big Bang. In that flash of energy, all sorts of exotic, heavy particles can be created, particles that haven't existed freely in the universe for billions of years. And just maybe, if you do this enough times, you might create a Higgs boson. The problem is, creating a Higgs boson is an incredibly rare event. You have to sift through the debris of trillions upon trillions of collisions to find the signature of just one. It's like trying to find one specific person's whisper in the roar of a sold-out football stadium. To do this sifting, scientists built two gigantic detectors around the collision points, named ATLAS and CMS. These detectors are marvels of engineering. They are the size of multi-story buildings and are packed with layers of advanced electronics. They are essentially massive, three-dimensional digital cameras designed to track the path, energy, and charge of every particle that flies out from the collision. The process works like this. The protons collide. A Higgs boson might be created. It exists for an impossibly short time and then decays. It can decay in several ways, but a couple of key patterns were what scientists were looking for. For example, it might decay into two high-energy photons, or it might decay into four muons, which are like heavy cousins of the electron. Well, the detectors can't see the Higgs, but they can see the photons or the muons that fly out. So the scientist's job was to comb through the data from billions of collisions every second. They would measure the energy and trajectory of all the debris. Then, they would try to work backward to see if a set of particles, like two photons, came from the decay of a single, heavier parent particle. If the Higgs boson exists and has a specific mass, then you would expect to see a small but consistent excess of these decay products at that particular mass energy. For years, they collected data, they smashed protons together, recorded the results, and analyzed. It was a painstaking process, involving thousands of physicists and engineers from all over the world. They were looking for a tiny bump on a graph, a small surplus of events that couldn't be explained by any other known process. And then, they found it. On July 4th, 2012, scientists at CERN held a seminar to announce their results. The room was packed. Physicists around the world were watching via webcast. The leaders of both the ATLAS and CMS experiments presented their data. And both experiments showed the same thing, a clear, undeniable bump in their data at a mass of around 125 giga-electron volts. They had found a new particle, a particle consistent with the properties of the long-sought Higgs boson. Peter Higgs himself, the man who had proposed the idea almost 50 years earlier, was in the audience. He was 83 years old. As the results were presented, he was seen wiping a tear from his eye. It was a historic moment, the culmination of a half-century of theoretical work and decades of experimental effort. The last missing piece of the Standard Model had been found. So, that's what the Higgs boson is and how it was found. But the second part of the question is just as important. Why does it matter? Why spend billions of dollars and decades of effort to find one tiny, fleeting particle? The first and most immediate reason is that it validates the Standard Model. This theory, which describes the fundamental workings of the universe, was incomplete. The Higgs mechanism was the keystone holding the whole structure up. Finding the boson proved the mechanism was real. It meant that our entire understanding of particle physics for the past 50 years was on the right track. It was a moment of profound confirmation. It's hard to overstate how important this was. Without the Higgs, the whole model would have collapsed. And we would have had to go back to the drawing board to understand the fundamental forces of nature. The second reason it matters is more profound. It explains our own existence. As we talked about before, the Higgs field is the reason particles have mass. Without mass, there are no atoms. Without atoms, there is no structure, no galaxies, no stars, no planets, no life. The fact that you are a solid object, that you can sit in a chair that the Earth holds together under your feet, is all thanks to the Higgs field. It gives the universe its texture, its substance. The discovery of the Higgs boson was the discovery of the source of that substance. No, it's not just some esoteric particle in a lab. Its effect is what allows reality as we know it to exist. The third reason is a little more subtle, but just as fundamental. It helps explain why the forces of nature behave so differently. We know of four fundamental forces: gravity, the strong nuclear force which holds atomic nuclei together, the weak nuclear force responsible for radioactive decay, and electromagnetism. In the very early high-energy universe, physicists believed the weak force and the electromagnetic force were actually two aspects of a single, unified force called the electroweak force. As the universe cooled down just after the Big Bang, something happened to break this symmetry. The Higgs field turned on. When it did, it gave mass to the particles that carry the weak force, the W and Z bosons. But it left the particle that carries the electromagnetic force, the photon, massless. This had a huge consequence because the W and Z bosons are so heavy they can't travel very far. This makes the weak force have a very short range, confined to the scale of an atomic nucleus. The photon, being massless, can travel forever. This gives electromagnetism an infinite range. So the Higgs field is responsible for splitting one force into two very different ones. It explains the fundamental asymmetry we see in the universe today. Without this symmetry breaking, the laws of physics would be very different, and again, life as we know it could not exist. The sun wouldn't be able to fuse hydrogen into helium through weak force interactions, so it wouldn't shine. The universe would be a dark, uninteresting place, but the story doesn't end with the discovery. In science, every answer leads to new questions. Finding the Higgs boson was the end of one chapter, but it was the beginning of another. And the new questions are even deeper. One of the biggest puzzles is called the hierarchy problem. The Higgs boson has a mass of about 125 GeV, but according to our theories, quantum effects should make its mass much, much heavier, trillions of times heavier. For its mass to be what it is, it seems to require an incredible, unnatural fine-tuning of the laws of physics. It's like balancing a pencil on its sharpest point. It's possible, but it seems incredibly unlikely and unstable. This suggests that there might be some other unknown physics at play that is protecting the Higgs boson's mass and keeping it light. Theories like supersymmetry or the idea of extra dimensions were proposed to solve this, but so far the LHC has found no evidence for them. The lightness of the Higgs remains a deep mystery. Another huge question is dark matter and dark energy. All the particles of the Standard Model, including the Higgs boson, only make up about 5% of the total mass and energy of the universe. The other 95% is a complete mystery. About 27% is thought to be dark matter, an invisible substance that provides the gravitational scaffolding for galaxies. About 68% is dark energy, a mysterious force that is causing the expansion of the universe to accelerate. The Higgs boson doesn't tell us what these things are. The Standard Model is a theory of the 5% we can see, not the 95% we can't. The Higgs discovery completed the model of the visible universe, but in doing so, it highlighted just how much we still don't know. There are other puzzles, too. For example, the Higgs field doesn't seem to explain the mass of neutrinos properly. Neutrinos are tiny, ghost-like particles that barely interact with anything. For a long time, we thought they were massless, but we now know they have a very, very small mass. The standard Higgs mechanism can't easily account for why their mass is so much smaller than that of any other particle. This might be a clue that there's more to the story of mass than just the Higgs field we currently understand. And finally, there's the question of the Higgs boson itself. Is it the only one? Is it exactly the particle the Standard Model predicts, or are its properties slightly different? Physicists at the LHC are now in the process of meticulously measuring the Higgs boson. They are trying to see exactly how it interacts with other particles, how it's produced, and how it decays. If they find any tiny deviation from the predictions of the Standard Model, it would be a crack in the theory. It would be a signpost pointing toward a new, deeper level of physics. So far, the Higgs boson has behaved exactly as the theory says it should. It seems to be the simplest possible version of the Higgs boson, but the measurements will get more and more precise in the coming years. Scientists are still hunting for clues. In the end, the Higgs boson matters because it's a window into the fundamental nature of reality. It's not just another particle on a list, it's the physical manifestation of a field that sculpts the universe. This field is the reason the world has substance and structure. Its discovery was a monumental achievement of human curiosity and collaboration. It answered a question that had puzzled scientists for decades, but it also left us on the shore of a much larger ocean of ignorance. We've completed a map of our little island, the 5% of the universe we understand. But the discovery of the Higgs boson has made the vast, dark ocean of the other 95% look even more mysterious. It solved one profound problem only to leave us with even more profound ones, and that, in many ways, is the whole point of science. The search never really ends. Each discovery is just a base camp for the next, even greater, expedition into the unknown. The Higgs boson wasn't an endpoint, it was a new beginning.